So today is review day, so we'll talk about whatever you want to talk about. I don't think that light really made any difference. Okay. That a little bit. Okay. So what do you want to talk about?
I didn't understand like the last 4 on homework 9.
Okay.
I was kind of lost.
All right. Well, then let's look at homework 9. Bring up the problems. Sure. Okay. So we'll look at the last 4. All right. Let me make this full screen. What does it say? Find 2 power series of the given. Find 2 power series solutions of the given differential equation about the ordinary point x equals 0. Okay, so write out the differential equation. Let's start a new canvas. Y double prime minus 2x y prime plus y equals 0. Okay. So first of all, when it says that this is an ordinary point, in the general form of these, we always have the sort of leading term in the ordinary differential equation, and there's some function multiplied by it, there's some coefficient that we called capital P of x. In this case, it's just 1. So when we divide through by that, so that the leading coefficient in this ODE is 1, do we get any division by 0 at any points x? So it's already 1. We have nothing, none of the other, this thing divided by P of x and this thing divided by P of x. None of those are going to be 0, dividing by 0 at 0. So just a review of what it means for it to be an ordinary point. Okay, so just diving right in, what do we have for our solutions? So we make the assumption that it's of the form y of x equals the sum from n equals 0 to infinity, a n x to the n. We take the derivative of this. And we get this. And then we take the second derivative. Get this. And then what we're going to do is plug all these in, equate the coefficients on like terms, and get a recurrence relation that will allow us to figure out what the coefficients are in this power series. So in order to do that, we want to make sure that all of the x to some powers are all to the same power. So the way that we do that is, should have done this maybe something like that. Okay. So y of x doesn't need to change, but y prime of x needs to be rewritten. And let's just write it beneath it. It needs to be rewritten so that instead of having x to the n minus 1, we have x to the n. So we're going to do a shift of indices. So if n starts off at 1, then n minus 1 is 0, which is what we want. But we want x to the n to be 0. So we start off at 0 instead. And then if n starts off at 1, then we want that to be n plus 1. So essentially, we're replacing everywhere that n appears with n plus 1. We're re-indexing this, and then x to the n minus 1 just becomes x to the n. So now we have it in the form that we want. Y double prime of x is equal to sum from n equals 2 to infinity, n times n minus 1, a n x to the n minus 2. So we can do the same thing rewriting this here. We'll start from 0 so that x to the n minus 2 becomes x to the n. And we're replacing all n's with n plus 2's. So that becomes n plus 2. This becomes n plus 1, a n plus 2, x to the n. And when we put these into our equation, what do we get? We get sum from n equals 0 to infinity, n plus 2, n plus 1, a n plus 2, x to the n, minus 2x times sum from n equals 0 to infinity, n plus 1, a n plus 1 x to the n, plus sum from n equals 0 to infinity, a n x to the n. This is all equal to 0. Now I need to combine that minus 2x into my power series there, the second one. And so what I get for this, the first one can stay the same. I'll just copy it down. Infinity looks terrible. Much better. N plus 2, n plus 1, a n plus 2, x to the n. Plus, I'm going to move the whole thing inside. So this is going to become sum from n equals 0 to infinity, minus 2 times n plus 1, a n plus 1, x to the n plus 1, because we got an extra x too. And you'll see I'm doing this in multiple steps, and it involves a lot of copying down the things that don't change. So it's possible to sort of elide some of those steps, but I'm not going to do that today. I'm just going to do it in a careful way. Okay, now when we move that x inside, we got an x to the n plus 1, so we need to shift things around. When we start from n equals 0, we get x to the n equals 1. Or sorry, x to the n plus 1. So when we start off at 0, this first term is x, the 1. So we need to rewrite that one. Okay, again, the first one doesn't change. I probably could have just pulled that term off by itself, rewrote it. Maybe I'll do that in the next problem. Anyway, so we're going to start from 1 now and make that x to the n. So n plus 1, if we're starting from 0, n plus 1 is 1. Now we're starting from 1, so we just need n to make that one start off at 1. And so everywhere we're replacing n with n minus 1. So that becomes a n x to the n plus sum from n equals 0 to infinity a n x to the n 0. Now, something that I've found is kind of helpful is that I will make sure that all of these series start off at the same value for the index by pulling out the initial terms. So if I pull out the 0 term for the first and the third series here, what I get is the first one is, let's see, plug in 0, I get 2 times 1, a2, 2a2, x to the 0. And then in the last one, I get a0 x to 0. So that's pulling out the 0th term from this one and this one. And now they can all start at n equals 1, and I can just combine them all together. Now they all have the same x to the n. They all start at the same index. So let's just throw them all together. What do we get? We get n plus 2, n plus 1, a n plus 2, minus 2, n, a n, plus a n, x to the n. I'm getting to the edge of the screen, so the tablet is. This is the last day that I'll be using this tablet. I have to return it to the university. So very happy to just get rid of this. Okay, so now we have this kind of separated out. Excuse me, hang on just a second. I've been packing up, and so there's tons of dust in the air here. Okay, I'm back. So for the, I do this n equals 0 case separately. Oftentimes, the separated case ends up being just a general case of the, or just a specific of the general case. But just in case that doesn't work out, let's say 2a2 plus a0 equals 0. Or in other words, a2 is equal to negative 1/2 0. So this will give us, ordinarily when we do these problems, the a0 and a1 will be arbitrary constants, and everything else will be determined in terms of those. So this gives us a2 in terms of a0. Okay, now for the rest of them, what we'll have is n plus 2 times n plus 1, a n plus 2. And let's rewrite this. Let's combine the like terms for the a n. So that's going to be 1 minus 2n, a n equals 0. And I'm going to do a couple of rewriting steps in order to make this easier to deal with. Subtract that second term over the other side. I get n plus 2 times n plus 1, a n plus 2 equals the negative of that. I'll just move that into the parentheses and make it like this. A n. And then divide this over the other side. I'll get a n plus 2 equals 2n minus 1 divided by n plus 2 times n plus 1 a n. And then I do a final rewriting step to get a n in terms of the previous ones. So I know that I'm going to want a0 and a1 are going to be arbitrary, but then I'll want a2, a3, and a4 to solve this. I think that's what it says. Write the first 4 non-zero terms. So I'm going to want A2, A3, A4, and A5. And so I want to rewrite this in terms that I can say A n is equal to, and then I just plug in the n, and I get my answer. So, all right, A n. Now, what I'm doing is I'm replacing all of the n's with n minus 2. So I get 2 n minus 2 minus 1 over n plus 2, n minus 2 plus 2, that's n. And this becomes n minus 1, a n minus 2. And finally, 2n minus 4 minus 1, that's minus 5, over n minus 1, a n minus 2. Okay. So this gives me my recurrence relation, with possibly the exception of what happens whenever n is equal to 0. So let's plug that in and see what happens. Yep, we have a problem. We would have a division by 0. So we get around that problem. We would have that when n equals 1 as well. No. I'm sorry. The problem, A0 and A1 are arbitrary. So we don't get those from this equation. So the fact that we're dividing by 0 when n is equal to 0 or 1 doesn't matter. It's when we're getting A2. So what happens there? In that case, we have, let's see, 2. So that's 4 minus 5, that's negative 1. The denominator would be 2 times 1, so negative 1/2 times A0. Okay, so in this case, we would have had no problem. This is just a specific case of this general recurrence relation. Okay, so we can just completely ignore that initial part that we did and just come down here to the recurrence relation. Okay, so now I'm going to do what might seem like a counterintuitive step. I'm going to go ahead and write out the general solution. And the general solution was, you remember, it was like this. Well, A0 plus A1x plus A2x squared plus A3x cubed, and so on. So that's what we're trying to do. We're trying to get the first 4 non-zero terms for 2 of these solutions. So I'm going to write the general solution, and then I'm going to split it up into two independent solutions. You'll see how I do that. So we're looking at this equation. If we have A0 and A1, then we can always get, well, for example, if we have A0, then we can use this equation to get A2, and we can use A2 to get A4, A6, so on. If we have A1, we can get A3, A5, A7, and so on. So A0 and A1 are going to be arbitrary, and now we're going to get A2. And we already saw that A2 is going to be negative 1/2 A0. I'm going to write it as minus 1/2 A0 x squared. Now A3, excuse me, is going to be 6 minus 5. That's 1 in the numerator. 3 times 2, that's 6 in the denominator, times a n minus 2, so that's A1. So plus 1/6 A1 x cubed. A4 is going to be 8 minus 5, that's 3, over 4 times 3, that's 12. A2, 1/4 A2, and A2 is negative 1/2 A0, so that's negative 1/8 A0. Now, I don't quite have this. This looks like I have a lot of terms here, more than the initial 4 terms, but I want to get 2 solutions. One of them that's just multiplied by A0 and one of them that's just multiplied by A1. So right now I have three terms that include an A0. So I need one more. And I have two terms that include an A1. So I need to keep going. A5 is equal to 10 minus 5. Here we go. Hopefully that's my tablet grew up for the day, and we'll be done with them. So 5 times 4, that's 20. A3, so that's 1/4 times A3, or 1/24 A1, right? Yes. X to the 5th. And the next one should be 4 of the A0 terms. So A6 is equal to 12 minus 5 is 7. 6 times 5 is 30. A4. Now A4 is 7/30 times -1/8. A0. Okay, so this is minus 7 240th A0. So minus 7 over 240 A0 x to the 6th. And then one more should give us enough terms. A7 is equal to, I lost my recurrence relation, 14 minus 5, sorry, 11 for 42 times A5. And so that's 11 over 42 times 1 over 24 A1. And can I work this out? I can scroll my recurrence relation off because I'm done with it. So what's 42 times 24? Well, 42 times 3 is 126. And then double that, that's 252. And then double it again, that's 504. And double it again, that's 1008. 1008. Now this, it feels like I've maybe made an arithmetic error, which you probably wouldn't make because you would have access to a calculator, but I'm not using it. I'm stubborn. Okay, and then I'll just write plus ellipsis. Say there are more terms. We know how to get them. We have our rule. Let me double check. I actually already did this problem. Let me see if I got the same answer. I did not get the same answer. 1/6, 1/24, 1 over 112. Okay, I clearly made a mistake in the arithmetic on the last one. Only the last one, though. All right, let's see
I
if I
think the numerator should be 9, not 11.
Very good. So 9 over, you think correctly. 9 over 42. Well, let's write it as 9 over 7 times 6. So that's 3 over 14 times A5. So what was A5? 1 over 24. A1. 3 times 8. Okay. Now, 14 times 8. Well, 7 times 8 is 56, and double that is 112. All right. Okay, so now the two solutions. I'm going to have one of them that has a zeros in it, so I'm going to factor that out, and I get 1 minus 1/2 a zero. Sorry, not a zero, x squared, minus 1/8 x to the fourth, minus 7 over 240 x to the sixth, plus dot dot dot. And the web work includes the plus dot dot plus a1 x plus 1/6 x cubed, 1 over 24 x to the fifth, plus 1 over 112 x to the 1 over 112 times x to the seventh, plus dot dot dot, plus ellipsis. And so these are our two solutions. There's one here and one here, and then every other solution to this equation can be written as a linear combination of those. Anyway, that's how you do these problems. Okay, so the next one. It's very much the same thing. So maybe I'll try to elide some of the steps together to get this one. Let's do this one in blue. Y double prime plus x squared y prime plus xy equals 0. And so if you've done this a number of times, you remember this first step, what I did was I took my y prime, and y double prime, and I made all of the powers of x to the n. Well, that step is always the same for every one of these problems. So I can just jump straight into that and say this is equal to sum from n equals 0 to infinity, n plus 2 times n plus 1, a n plus 2 the n, plus x squared. Well, let's go ahead and do this one. N equals 0 to infinity, n plus 1, a n plus 1. This would be x to the n, but we've got an extra x squared there, so we get x to the n plus 2. Plus n equals 0 to infinity. Nope. A n x to the n plus 1. So I've done a lot in one step. I've re-indexed it so they all started at x to the n, and then I moved the powers of x's inside the power series. So now they're no longer all at x to the n, but I did a couple of steps in one there. Okay, so now rewriting these things so that they all have x to the n, n plus 2, n plus 1, a n plus 2, x to the n, plus, and we start at 1, and we replace all the n's with n minus n, a n. Oh, no, sorry. We need to start at 2. We have x to the n plus 2. So this will become n minus 1, because we're going to replace all the n's with n minus 2. A n minus 1, x to the n, and then finally n equals 1, infinity, a n minus 1, x n. Now I'll peel off my initial two terms from the first one. So plugging in a 0, I get 2 a2 plus, let's see, 1, that's 3 times 2, 6 a3 x. So now this one will start at n equals 2. And then the last one, sorry, I said this one, I meant this one. The last one, I'm going to peel off the n equals 1 term. So I get a0 x. Yep. Okay. And now everything else. N equals 2, or sorry, n plus 2, n plus 1, an plus 2, plus n minus 1, an minus 1, plus an minus 1, xn, all equals 0. So all the coefficients on like terms have to add up to 0. What do I get from this? Well, for the x terms, I'm sorry, for the constant terms, I only have 2a2 is equal to 0. That's my n equals 0 term there. So do that in red like I did last time. So this is the n equals 0 case. 2a2 is equal to 0. So what we get from this is just a2 is equal to 0. So we have a2. Now, for the x term, n equals 1, what do we have? So we have 6a3 plus a0 equals 0. So in other words, a3 is equal to negative 1/6 a0. And then the general recurrence relation will be n plus 2, n plus 1, an plus 2, plus n minus 1, an minus 1, plus an 0. And actually, sorry, that should have been an an minus 1. I'm going to combine these last two terms because we have an n minus 1 plus 1. So just copy down the first one. An plus 2 plus n an minus 1 equals 0. Now I'll move that over to the other side. I'll get, well, let's do it all in one step. N over n plus 2, n plus 1, an minus 1. And then the final step, for my convenience, I'm going to shift all of the indices. Sorry, I don't have you on the screen. I'm going to shift all the indices down by 2 so that I start, instead of at an plus 2, I have an. That means I'm replacing all the n's with n minus 2. It becomes n minus 2, n minus 1, an minus 3. And so you see what we get from this is we have a 0, we get a 3, and then a 6, and a 9, so on. We have a 1, we get a 4, a 7, a 10, and so on. All of these depend on the 1, 3 before it. And finally, a2 is equal to 0. And so we get a5 is equal to 0, a8 equal to 0, so on. Okay. Now, I'm going to double check my recurrence relation. Now, this one is fundamental. I'm going to write that down here. A2 is equal to 0. We can't get that one from the recurrence relation. That one just won't come from it. This is one of those special cases where you don't get that one. Now, n equals 1. Well, that one gives us our a3 term. So do we get our a3 from a0 properly? So 3, we plug in. We get 1 for a numerator. Uh-oh. Did I make a mistake? double check this and make sure I didn't make a mistake here. Negative 1,680. Hmm. And we get 1/6 from this recurrence relation. Did I make a mistake there? I bet I did. Yeah, I did, didn't I? When I subtracted this n over, I didn't make it a negative. Okay. So we checked against our previous work and found that let's just make this so we want n negative n when we subtract. We replace n with n minus 2, we get negative n minus 2, which is 2 minus n. Okay, there we go. Forgot what I was going to say there. Oh, we checked against our previous work and we found a mistake. That's good. Okay, anyway, so that gives us our n equals 1 case. And so everything is included in this recurrence relation here. We can scroll everything else off the screen. Don't need that anymore. All right, now we can start figuring out what our coefficients are. So A0 and A1 are arbitrary. Don't have to write this out, but I am. A2 is equal to 0. And so A3 is the first one that we don't have. So that's -1. I think this is a little bit easier for my brain to deal with if I write it as negative n minus 2. I don't know about you, but that's a little bit easier for me to think about. So it's -3 minus 2, so that's -1 over 6A0, which is what we had before. So let's start writing this out. We get y of x is equal to A0 plus A1x, no x squared term, and we get minus 1/6 A0 x cubed. Now A4. So that's -2 over 12. Yeah. A1. So this is negative 1/6 A1. X to the 4th. Okay, so I've got 2 of each. A5 is -3 over 20. A2 is 0. I could have just skipped that one, right? A6, I'll get it next time. -4 over 6 times 5. We'll go ahead and write it as 30. A3. So this is negative 2/15 times negative 1/6 A0. And so that gives me 1/45 A0. And this time, don't wait till the end to tell me that I got it wrong. I got it wrong. I know it's a fun surprise for me to, find my own mistakes, but trying to get through some problems here today. Okay, A7. Let's do A7 next. So that's going to be, let me screen back, -5 over, let's just write it as 7 times 6. We'll do the math at the end. A4. So this is -5, 7 times, I should have just written down what A4 was. -1/6 A1. Right? Okay. 5 over 42 times 6. 126 times 3 is 126. And then double that is 252. How many do we have? 1, 2, 3. 1, 2, 3. Okay, one more of each. A is 0. A9 is -7 over 9 times 8 times A6. 1 over 45. These numbers are getting painfully large. Has anyone noticed an arithmetic mistake yet? Are you ready to save me from myself? Okay, 9 times 8 times 45. So 45 is 9 times 5. I want to do this one in my head. Oh, hey, maybe it's not so bad. So 9 times 9 is 81. And 81 times 40, so 81 times 4 is what? Double 81, that's 162. 324. 3240. Not so bad. You do the mental math trick. Maybe this one said only the first 3 terms. Yeah, it did. Okay. Great. Let's stop there. So what are our 2 solutions? So let's move this, block this off. A0 times 1 minus 1/6 x cubed plus 1/45 x to the 6th plus ellipsis plus A1 x minus 1/6 x to the 4th plus 5 over 252. How would you say that? 5 252th x to the 7th plus ellipsis. Okay, so we've got our 2 solutions. Now, I wanted to make sure to do the last one today, so we'll skip to that one, and then you're not sick of it yet. Oh, problem 10 is actually the interesting one, so we should come back to that. All right. Find 2 power series. All right, write 4 terms. Okay, same thing. Do green this time. Y double prime plus 1 plus x y is equal to 0. So I'm going to jump straight into it. Equals 0 to infinity, n plus 2 plus 1 plus, so from n equals 0 to infinity, a n x to the n. So that's the 1 times y. And then the x times y is going to be, I'm not going to do this one in my head. So that's what we get. Now I'm going to have to shift this one. Maybe that's not too bad. Plus 2, plus 1. I left about a bunch of stuff here. an plus 2, x to the n, plus n equals 0, infinity, an x to the n, plus sum from n equals 1 to infinity, an minus 1 to the n. Okay, now I'm going to peel off the first terms. When it's 0, it's 2a2 plus, and now the second power series, when it's 0, it's a0 plus sum from n equals 1 to infinity, n plus 2 times n plus 1 times an plus 2. Just give me 1 second again. All right, I have recovered. Plus an plus an minus 1. This is a kind of interesting one too. And this is equal to 0. Okay, all the other stuff that we've written, we can now discard because this is going to give us our recurrence relation. So the n equals 2, n equals 0 case, well, that'll give us a2. So we get 2 an plus a0 equals 0. Basically, we're looking at the constant coefficients. And that again gives us a0 equals minus 1/2. Sorry, a2 equals minus 0. Now the general recurrence relation is n plus 2 times n plus 1, an plus 2 plus an plus an minus 1 equals 0, or an plus 2 equals negative a, let's do a negative in front, an plus an minus 1 over n plus 2, n plus 1. Right? And now what happens? Well, let's do that final rewriting step. An equals negative an minus 2 plus an minus 3. Bad. N times minus 1. We're going to have to look at this part over and over. I want to make it a pain on our eyes. Save your future self from a little bit of trouble. Okay, now does that specific n equals, I wrote n equals 0 or n equals 2, it should be n equals 0. It doesn't really matter, it's just a note to self. Okay. Worrying about unimportant things. So when we plug in n equals 2, what do we get? Well, we get a0 plus a negative 1. Now, if we kind of adopt the convention that a subscript negative 1 is 0, then this does work out. So I'm just going to say this is the only thing that we need to preserve from all of that work. Everything else can be thrown away. So we get y of x is equal to a0 plus a1x. Okay, those are always the same. And then, well, let's just throw that one on there. We already got it. Minus 1/2 a0x squared. Now we can continue. So that's a2. So the next one that we want is a3. And that is going to be negative. All right. Gather all of our energy here. And we write that down, actually. A2, because we're going to have to refer to it later. Okay, A3 is going to be 3 minus 2, so that's A1 plus A0 negative over 6. All right. So I'm going to say this is negative 1/6 A0 minus 1/6 A1. Let's write it like that. Negative 1/6 A0 minus 1/6 A1 x cubed. I'm going to go to the next line. Make a little division here between our work and our solution. A4, more clear. A4 is equal to negative A2 plus A1 over 4 times 3. There might be some cancellation. Okay, now actually, I am going to write this. I'm going to change a little bit how I'm writing. Negative 1/12 times A2 plus A1. That way I can distribute it out a little easier. So A2, that was negative 1/2, so this is 1/24 A0, and then negative 1/12 times A1, just A1. Negative 1/12 A1. So this is 1/24 A0 minus 1/12 A1. And I'm going to try to write these general terms. Let's see, we got A0, 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 so that's 4 of them. Now A1, A1, A1. We need one more. A5. I'm trying to write them in the order A0, A1. So in the next step, it'll be easy to separate those out. All right, this is 1 over 5 times 4, 1/20th. A3 plus A2. So that's negative 1/6. So that's 1/120th A1. And I guess we kind of don't care about the A0 term, but let's write it A2. So that's plus 1/40th A0. Yeah, let's write it out. 1/40th A0 plus 1/20th A1 x to the 5th plus ellipsis. Okay. Now I'm going to go straight to writing this down as two solutions. I'll write as y1x. Actually, don't need the superscript here. That was something we introduced for the systems, where our thing is a vector. Okay, so the A0 one is going to be, okay, calm down. 1 1, sometimes you just have to laugh about it. 1/2 x squared minus 1/6 x cubed plus 1/24 x to the 4th. And WebWork isn't asking for it, but we computed it, so we might as well. They're not asking for it, but we might as well write it down because we went through the work of getting it. Why not? We deserve it. Now, The next one is x minus 1/6 x cubed minus 1/12 x to the fourth plus 1/120th x to the fifth plus ellipsis. And that'll be our two solutions. There we go, highlighted. Beautiful. Now, let's go ahead and do this one. So if you're sick of it, you can leave. But if you're not sick of it, then why not stay? So this is the this is officially the last problem that I will be working in this class. Not you. You'll be working more on the final exam, but I won't. Okay. Last one. X squared plus 1. Just writing down the problem. Actually, let's go ahead and have a little fun. We'll move it over the other side. It was negative already. Okay. We know what the series is going to be. N plus 2. Now the first one I'm going to do n plus 2 because of that x squared. And then I'm going to have n equals 0 to infinity, n plus 2, n plus 1, n plus 2, x to the n equals 6 n x to the n. And now I only have one of them that I need to rewrite in my next step. Sum from n equals 0 to infinity, n plus 2, plus 1, 2. I was just kind of joking around about that. I think it's really a good idea. You know, you built up these skills over time. If not the first one, I need to copy down. I should have not been trying to pass on some wisdom. I should have been concentrating on the problem. Let me concentrate on the problem for a second, and then I'll enjoy the sound of my own voice for a minute. Okay, so this is all equal to this. I was just joking about the, you know, I'll never work these problems ever again. It's good. It's when you build up a skill like this, you spend a whole summer semester working on this. Don't let it go to waste. You know, spend a little time, just a little exercise, a little mental exercise. See if you can still do these things. Good for your brain. And you know, you never know, you could have make a little money on the side by tutoring people for this class. Something to think about. Okay, we've got all x to the n's now, but we have a extra. We're starting off n equals 2, so let's peel off a few terms here. We will get on this side n equals 0, so that's 2a2 plus 6a3 x. So that's from this power series peeling off the first two terms. And then the other power series I'll leave as is. And then this one over here, we get 6a0 plus 6a1 x plus the sum from n equals 2 to infinity 6an. All right, so we'll do the a zeros. We get, I'm sorry, the constant terms. 2a2 equals 6a0. In other words, a2 is equal to 3a0. So that's the constant terms. Now the linear terms, 6a3 is equal to 6a1. In other words, 3 is equal to a. And then the general recurrence relation. N times n minus 1, an equals 6n. I missed something? Yeah, it doesn't make sense, does it? Must have messed something up here. Oh yeah, I made a big mistake. I made a huge mistake. I completely left off one of these. I got that one. I didn't get this one. So let's throw it in right here. N plus 2, n plus 1, an plus 2, x to n. All right. So it's going to be n plus 2, n plus 1, an plus 2, plus n times n minus 1, an equal to 6 an. Double checking. Okay. Now I'm going to subtract the an's over the other side. To get, well, I'll expand that out. That's n squared minus n plus 6. So it's going to be negative n squared minus n plus 6 times an. I'm going to factor out a negative from that here. So we'll do an plus 2 equals minus n squared plus n minus 6 over n plus 2. You know what? Maybe that's not the best idea because we're going to have to re-index this. We don't have to, but it's a nice step, I think. Let's just write it as minus n times n minus 1 plus 6 an. And then an plus 2 is equal to minus n minus 1 plus 6 over n plus 2 times plus 1. A. Now I'll do a re-indexing step. An is equal to, I'm replacing n with n minus 2, so that's minus n minus 2 times n minus 3 plus 6 over n minus 1, an minus 2. And now I'll kind of fix the numerator. So that's negative. I'll pull the negative out. That'll become minus 6, and it'll become n squared minus 5n plus 6 minus 6 over n times n minus 1, an minus 2. So this is equal to negative n times n minus 5 over n times n minus 1. That seems familiar. Minus n minus 5 over n minus 1, a n minus 2. Now let me double check this. I think that's right. They did work this one out. See if I can find it. Probably not. Oh no, here it is. Oh, I just left it as 6 minus n minus 2 times n minus 3. I didn't go through the step of noticing that that's simplified. Okay, cool. Anyway, A0 and A1 are arbitrary. A2, might as well copy it down. A2 is equal to 3A0. A3 is equal to A1. Is that what we get from this? So if we plug in, oh, let's write this. Let's rewrite this as a, just a statement by itself that we can scroll all this other stuff off. Okay, so A2 we said was 3A0. So what happens when we plug in 2? We get negative 3 over 1, negative of negative 3, A0. Okay, so that one works. So we can ignore that. And then 3, what happens? So we get negative 2 over 2. The negative of that is 1, A1. Okay. So everything works with this. So we can get rid of all of this stuff and move up here. And now let's start writing out our solution. Y of x equals A0 plus A1x plus, we already had A2 and A3, so that was 3A0. So let's just write out A2 is 3A0, A3 is A1. Okay. And then let's see, so that's plus 3A0 x squared plus A1 x cubed plus now A4. That's going to be negative 1 over 3, 1/3 A2. So that is A0. Oh, interesting. Plus A5. Now this is when the really interesting thing happens, because what we're going to get is 0. We're going to have n minus 5, so that'll be 0. And then those are going to be zeros from then on, right? So we're no longer going to have any A1 terms. All those odd numbered terms are going to be zeros. So we do need actually one more, I think, for web work. So that's negative 1/5 A4. So that's negative 1/5 A0. And we have 1, 2, 3. I think that's enough. Okay. So we have two solutions. Y1 is going to be the A0 one. So that'll be 1 plus 3x squared plus x to the fourth minus 1, did it again, minus 1/5 x to the fifth, and so forth. And y2 is in fact going to be x plus x cubed. That's it. Stops there. I'm going to double check my answer. Yeah, that's what I got before. Okay, so that's homework 9. That's how to do problems like that. There are problems like this on the final exam. I'll go ahead and tell you. Yeah, that's it. Well, unless you want to talk about some more stuff.
Do you think the final is like significantly harder than the homework?
I don't think so. I think it's well, I think it's probably about the same or maybe a little easier. I wouldn't be too worried about your grade in this class. I'm going to be pretty. I'm feeling generous. I'm feeling very.
Thank you.
Yeah. This is the very last. This is funny. This is the last class that I'm going to teach at UK. Like today, I'm done. I'm done with UK. I've got to grade the final exams and put the grades in the computer, and then and return this tablet and clean out my office, and I'm completely done. And return a library book. But when I took this class as an undergraduate, it was also the last class that professor was teaching at UK, retiring. This was in like 2000. I don't want to tell you how old I am. This was in 2004 or something. So I took that class. So he actually he retired immediately after finishing whatever he had to do for that. So he, at the end of the class, he was like, anybody who has an A so far in the class doesn't have to take the final. You just get an A for the class. So that was nice. So it's kind of like everything's coming full circle. Now I'm being the nice person teaching differential equations. Anyway, I remember absolutely nothing from that class. I had to reread everything. I had to relearn this entire class before I taught it. Anyway.
Yeah, I don't really know about Sarah, but like I don't know, the calculus of this class is just like so different from what I've done in the past. Like I've liked everything up to this point, and then this is just all very different. And
yeah,
I don't know.
It is like sort of the normal stuff that we work with is what you're trying to do. You're dealing with functions, and your answer that you're trying to get out is a number, right? Like you have some relationship. The function gives you some relationship between numbers. So this class is like one level of abstraction above that. So instead of having functions that tell us something about numbers, we have relationships among functions. And the answer isn't a number anymore, it's a function. We're trying to figure out what the function is. So it's like one level of abstraction up from that.
All right, well, thank you.
Yeah, no
Good
problem.
luck at your next job.
Thank you. I could use it. Goodbye.
Bye.
Bye.